Hello friends, I welcome you all in my sixth lecture in a series of in the sixth lecture on a series of generation of microwave signals. So here in this lecture we are going to see the one device that is called as crossfield amplifier that is used for the generation of microwave signals. So this crossfield amplifier, as the name suggests, it is an amplifying device and it takes an RF as an input signal and it amplifies the RF signal and gives it an output. Now this device is having a low gain and a low bandwidth as compared to the any other devices. But it is having a very high efficiency and high output power. So it is very commonly used device for practical applications. Now it is this crossfield amplifier is having a similar structure as that of a magnetron. Similarly, Similarly, it is having the electric field and a magnetic field perpendicular to each other. As the electric field and a magnetic fields are perpendicular to each other, it is called as cross-field amplifier. So, then as this is a cross-field amplifier and the electric field and a magnetic field are perpendicular to each other, it is having the similar structure as that of a magnetron. It is having cylindrical cathode, which is shown by a green color at the center, and it is having the number of anode cavities. Now, this number of anode cavities, for this number of anode cavities, input RF signal is supplied, and the output RF signal, which moving after this number of anode cavities, output RF signal will be collected at an output of cavity. Now, to give the insulation in between the RF input and output, insulating RF absorber is there, which is shown by a magenta color. Now, this RF field moves in a slow wave structure like a TWT, that is traveling wave tube. Now, these cavities are acting as in a slow wave structure. So, there is a more times the interaction in between the that is the electric field and the RF field will be number of interactions will get increased. As the number of interactions will get increased, then the velocity modulations takes place, number of velocity modulations increase, and number of velocity modulation increases, that means and the density of electron increases, and this density of electron increases means that is the energy outputted by the electron, kinetic energy increases, and this energy is given to the RF field. So as it is given to the RF field inside the cavity, the output power of an RF field increases, that can be taken at an output. Now see, to achieve all this, the movement of the electrons will be a spiral in between the cavities or in between the anode and cathode. So to achieve this spiral movement of the electron, the voltage as well as the RF field, that is a magnetic field, electric field and a magnetic field supplied to this device is controlled. Now you can see this device which is looking like the same as that of a magnetron. But it is having one input RF section and output RF section and RF absorber. Similarly, the lines which are shown in between the cathode and anode, these are the spiral lines. They are controlled by this is the path of electrons, and this is controlled by the electric field and a magnetic field. Now, this CFA has, as I told you, it is having lower gain and a bandwidth, but it is having a more efficient and capable of a higher output power. In the CFA, the magnetic field and electric field are perpendicular to each other. Then this is the same type of field interaction as that of a magnetron. But magnetron is an oscillating device. It is an amplifying device. So it is called as cross-field amplifier. Then the RF circuit is similar to that of the coupled cavity TWT RF circuit, or a slow wave structure we can call. The CFA has a useful property that when the power is shut off, the input simply passes to the output with a very little loss. This avoids the need of a RF bypass switching in the event of the failure. So This is a very useful property of is that is when the power is shut off, then we are getting an output power. So bypass switching in the event of a failure is not required. Now, if you are connected to two CFAs in a sequential, then when the one and if we are providing power to any one of the CFA or one of the CFA, and if it is one, then if one of the CFA is not working properly, then power can be removed from primary tube to the, or it can be applied to the secondary tube as a backup power. That is, failure doesn't affect the input and output signal. That is, if it is fail also, then also it can provide an input signal same as that of an output signal. So this this can be, yeah, act as a backup battery for the second CFA, first CFA if it is fails. This approach built a redundancy that was required in a downlink transmitter in the Apollo lunar module, or it is very efficient and reliability where the very high efficiency and reliability is needed. So it can be used in the Apollo lunar module, that is a satellite transmitter. So now we will see the working of it. When a large negative voltage is applied to the cathode, which is a green electrode at the center, and a large magnetic field is directed perpendicular to the electric field, that is perpendicular to the page. This forms a thin spinning disk of electrons. So because of this effect of large electric field and large magnetic field, electrons will take the path that I have already shown you in the diagram, and it will look like a spinning disk of electron. This part of electron in between the anode and cathode look like the spinning disk of electrons with a flow pattern like the spinning water as it drains from the sink or toilet. A slow wave structure is located above and below the spinning disk of electrons. The electrons flow much slower than the speed of light. Then the slow wave structure reduces the velocity of the input RF signal enough to match the electron velocity. The RF input is introduced into the slow wave structure. The alternating microwave field causes the electrons to alternatively speed up and slow down. These disturbances grows larger as the electrons spiral around the device. An electron slows down as the RF energy grows. This all means like that. That is, when the electrons is having a spinning like structure and the RF field is moving through the slow wave structure which is present at the top and bottom of the spinning disk of electrons, then the more number of interactions in between the RF field and the electrons are taking place, and this will this interaction results into the slowing down of the electrons, or it can increase the speed of the electrons. That is, it is creating a velocity modulation, that is positive. The electrons which are coming in the positive half cycle, effect of positive half cycle, velocity increases. Then the electrons which are coming in the effect of the negative half cycle, velocity decreases. So this slowing down or increasing, growing the electron velocity, that will result into the bunch of electrons, and this bunch of electrons naturally when they becomes a bunch, we are calling it as a density modulation. Now this density modulation slows down the electron, the velocity of electron, and this slows down means the electron release their kinetic energy. Now this released kinetic energy is catched by an RF field and the RF energy grows, and this produces an amplification. There is a very small amount of RF feedback from output to input. As we are connecting the RF absorber in between the output and input, so very small disturbance is there, and very small phase jitter in the device can be created because of this disturbance. This is about a cross field amplifier. Thank you.